Welcome to another CVB202 practical, the determination of copper by flame atomic absorption. It may seem a little odd to start a practical in the Brisbane City Botanical Gardens, but in this practical we are determining the copper level in the pond sediments in the park. It is quite common for an analytical chemist to be asked to sample and determine the level of pollutants in an environmental sample. Being the largest green space in the heart of Brisbane City, the park is frequented by many daily visitors. The park and the ponds are home to an amazing variety of animals, birds, fish and aquatic life. In fact, this abundant and diverse array of life is one of the draw cards for visitors in the park. Copper is ubiquitous in our daily lives due to its corrosion resistance and high thermal and electrical conductivity. While a little copper is essential, too much copper can lead to toxic effects such as Wilson's disease. Aquatic life is particularly sensitive to copper, with the LD50 dose typically in the order of parts per million. This is one of the main reasons copper is used as an algicide and anti-fouling agent in aquatic applications. If used in this way, copper might find its way into the pond. Other applications of copper that could lead to pond contamination are its use in plumbing and in the roofing of the nearby historical buildings. The roofs of these buildings have a brown-green patina due to the oxidation of the native copper roofing material. This oxidized copper may be blown by winds or washed by rain into the pond. To determine the copper level in the pond sediment, a sample of this sediment was taken by a grab sampler and filtered and dried according to the procedure in the practical manual. A sample of this sediment was weighed into a beaker using the weight by difference methodology.
So weight by difference is to find the actual mass that you've transferred into your sample, and you do that by recording your initial vial mass with your sample, and your final empty vial mass, and that way you can record any dregs that have been left over in the vial. In experiment 3, we have recorded the mass of our sample and our vial to be 4.7131 grams. We're now taking that vial with our sample and transferring it into our beaker that we're using, and then we can record the final mass of the empty vial without our sample to be 4.2151 grams.
Once the sample was weighed into a beaker, a solution of nitric acid was made. A 2 milliliter sample of concentrated nitric acid was placed into a beaker. To do this, a 2 milliliter Class B volumetric pipette was used. Using a measuring cylinder, 25 milliliters of water was measured out and mixed with the 2 milliliters of nitric acid. This acid solution was added to the sediment sample. The beaker now contained the nitric acid solution and the weighed sediment sample. This was placed on a heating mantle and gently boiled for 30 minutes. A filter paper was fluted and placed into a funnel located atop of a filter stand. A 100 ml Class A volumetric flask was placed under the filtration apparatus. After the acid and the sediment had cooled, it was filtered through the prepared filter apparatus. A stirring rod was used to guide the flow from the beaker into the filter. Once all the solution was in the funnel, the solution was quantitatively washed into the funnel. This utilized a glass rod placed on top of the beaker, and a stream of water from the wash bottle was used to ensure complete transfer of both the solution and the solids. This quantitative transfer technique is also demonstrated in the front of the CVB202 practical manual. Once the solution is filtered, the filter paper was washed, and then also the funnel. The solution was then made up to the mark with deionized water. A series of standards were made in labelled 100 ml Class A volumetric flasks. To make the solution, the required volume of 1000 ppm copper solution was pipetted using an autopipette into the flask. The autopipette was later calibrated, which will be demonstrated later on in this video. The standards were made to contain 0, 0.2, 0.4, 0.6, 0.8 and 1 ml of copper solution. To each standard solution, 2 ml of concentrated nitric acid is added using an autopipette. As you may remember from earlier in the video, 2 ml of acid was also used in the sample. Using the same volume of acid in the sample and the standards ensures that the matrices of these are identical. This is called matrix matching and reduces the interferences caused by the acid. Once the acid is added, these solutions were made up to the mark using deionized water. Once the sample and standards were prepared, it was time to run them on the flame atomic absorption spectrophotometer. The light source, flame, and nebulizer system are easily identified on the instrumentation, but most of the instrument remains hidden inside the spectrophotometer box. A double beam flame atomic spectrophotometer will consist of a hollow cathode lamp as a light source, rotating mirrors to redirect the light around the flame, a nebulizer system, a flame, a monochromator, and a detector. A hollow cathode lamp is a light source used for flame atomic absorption as it offers several advantages over other light sources. The absorption of light by atomic species occurs in very narrow wavelength ranges called lines. The widths of these absorption lines are smaller than a nanometer. This means that a light source that only emits these very narrow ranges is preferred. The cathode of a hollow cathode lamp is made from the analyte of interest. In this case, the cathode is made from copper. This means that when it's energized, the lamp produces predominantly emission lines applicable to copper. To do this, the lamp has a low pressure of neon atoms inside of it. These neon atoms are ionized by the voltage applied to the lamp and collide with the cathode. This causes the atoms of copper to be spluttered into the vapor state, which allows them to be excited by the applied voltage. When the atoms fall to their ground state, they emit light unique to the element emitting them. This matches the wavelength of the source to the required wavelength for the analysis. Once produced, the light is steered around the instrument using mirrors. The flame is where the sample is atomized and the absorption of light occurs. The flame is made by a slot burner which produces a flame which is thin. The burner can be moved backwards and forwards, up and down, and be rotated. This allows the analyst to optimize the flame temperature and level of oxidation and path length of the flame respectively. There are several processes that need to occur in the flame before absorption of light can occur. Initially, the sample is a solution, so desolvation of the sample must occur. This leaves the solid salt of the analyte, which must then be melted and then volatilized in the flame. Once the sample is in the gas state, the energy inside of the flame rips the molecular species into their constituent atoms. It is these atoms which then can absorb the incident light from the lamp. Obviously, for these processes to occur efficiently, the sample must be introduced evenly throughout the flame, so the flame can maintain its energy and be capable of accomplishing all of the steps together. To do this, the sample is introduced through a nebulizer. The nebulizer uses air that is required for the flame to shake off droplets from the tip of the nebulizer in the same way a spray gun works. If large, the droplets that are formed hit the impact bead and are either broken into smaller droplets or stick to the impact bead. Only the smallest droplets are small enough to make their way past the impact bead and through the baffles where the fuel for the flame is introduced. This means only a small part of the sample makes its way through to the flame and most finds its way into the waste. In this practical, each standard was run on the instrument from the most dilute to the most concentrated. Before each sample was run, the analyst shook the sample to ensure adequate mixing of the sample. Once the standards were run, the sample was then analyzed. The absorption of the standards was plotted with QT calib to ensure the QC of the regression was below 5%. To calibrate the autopipette, specific volumes of water were pipetted into a vial and weighed. The temperature of this water was measured, so the density of this water may be looked up in reference books such as the CRC Handbook of Physics and Chemistry. Several different volumes were used, so QT calib may be utilized to determine the real dispensed volume of water from the volume indicated on the pipette.